We have a few more review problems here in force, work, and energy. A mass is launched upward as shown. Here, air resistance is not negligible. Okay, that's probably significant. Between launch and the top, determine these things. The net work done on the mass. If air resistance is not negligible, that means that we can't use conservation of energy. Air resistance is essentially friction with the air. So we can't use conservation of energy. What else do we have at our disposal? I think we can use that the net work done equals the change in kinetic energy. That one applies even when we have friction. Can we figure this out? What's the change in kinetic energy? It's going to be 1/2 times the mass, which is given as 2. And what's V final? V final is 0, so I square that, minus V initial, which is given as 10. 10, square that. How much is that? Negative 100. Negative 100 joules. And that shouldn't surprise us that the work is negative, because whenever negative work is done, things slow down. And this mass has. What about the work done by gravity? The work done by gravity is always equal to the mass times g times the change in height. Whenever we're close to the Earth, I should say. If you're talking about satellites going great distances that compare favorably with the radius of the planet that is being circled, let's say, then we have to deal with that a different way. But that's a story for another day. For right now, we are close to the surface of the Earth. So the work done by gravity is going to have the magnitude m times g times h. And is this going to be positive or negative work? As this thing goes up, gravity is acting downward, so this is going to be negative work, and that looks to me like it's going to be negative 80. Let's finish by dealing with the work done by air resistance. The net work was negative 100 joules, and gravity did negative 80 of that, so air resistance must have done negative 20. And again, air resistance is always going to do negative work whenever a mass is moving through the air.